If I burn a piece of paper, I cannot unburn it. So that kind of processes are known as irreversible processes. No process is possible whose sole result is the absorption of heat from a reservoir and complete conversion of that into work. Piston is expanding isothermally. So again, there is an exchange of energy there, but the temperature is remaining constant. Keeping the energy constant, now the gas is going to expand adiabatically. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with thermodynamics. So let's see what the last session of thermodynamics holds for us. We discussed about the 0th law, first law, and now we are going to discuss what is the second law of thermodynamics, and luckily we don't have to study the third law. So this is the last law we are going to study in thermodynamics, and that is known as the second law of thermodynamics. Again, if we can say that the first law is relating to law of conservation of energy. If we can say that the first law deals with the conservation of energy, then we can say that the second law essentially states that time only moves forward. That is physics way of saying things. That is, second law is also known as the law of entropy, and we say that entropy, that is the disorder of a system, will always remain positive, or simply we say that any system tends to be more disordered, or it tends to be more disordered as time goes by. Entropy is always positive. But again, that is not the statement you have to study here today. Here we are going to study two different statements that together make the second law of thermodynamics. So what is that two statements? So the first statement you have to know is known as Kelvin-Planck statement. So what does Kelvin-Planck statement actually mean? It is actually formulated by Lord Kelvin and Max Planck. That is, their theories are formulated together and made this particular statement. That is, we say that no process is possible whose sole result is the absorption of heat from a reservoir and complete conversion of that into work. That is, 100% of energy 100% of energy cannot be converted into 100% of work. That is, if I give 100 joules of energy, then I cannot expect 100 joule of work to be done. That is because energy will be dissipated. Like if you give chemical energy to, let's say, a car, that is, you're giving petrol, or let it be an EV car. So we're giving electric energy to that particular EV car. Then what happens? That electrical energy, if you're giving 100% of electrical energy, then that is distributed to the motor. When the motor is running, it is actually converting that energy into mechanical energy, but it is not 100% converted. A part of that energy is lost as vibrational energy, frictional energy, and other sound energy and other forms of energy. So basically, When energy is given to a system, the system cannot use 100% of that energy to do a work. There will be different forms of losses. Like heat energy dissipation is one famous form of loss. So like that, energy cannot be 100% converted into work done. That is explained using this particular statement. That is Kelvin-Planck statement. And the second statement states that it is known as Clausius statement, which is found by Clausius, and Clausius stated that no process is possible whose sole result is the transfer of heat from colder body to hotter body. That is, if there are two systems and there is a difference in temperature, always heat will flow from the higher temperature to lower temperature. If there is a gradient, that is a difference, then heat flows from higher concentration to lower concentration, and the reverse is not possible. That is, from lower concentration to higher concentration, heat doesn't flow naturally. We can induce that like with the AC system, that is, we can reduce the temperature of a room again and again, but that is by using the compressor, mechanical arrangements and all that. But naturally, it is not possible. Heat only travels from higher concentration to lower concentration, and that is known as Clausius statement. And again, this again can be summarized into two words. You don't have to note down or anything, just understand that this can again be translated as the energy of the universe will always remain constant, or again one more way of saying it is that the entropy is always positive, or another way of saying it is that disorder of a system will always tend to maximum. You don't have to study or go into the details of entropy or anything. The second law of thermodynamics, for you there are only two statements, that is the Clausius statement and the Kelvin-Planck statement. So that is enough for you. So we don't have to dive deep into the world of entropy, because entropy itself is a very huge topic. So we don't have to dive deep into that particular statements right now. So that was all about second law of thermodynamics. Now what is reversible and irreversible process? So again, you know that there are many processes and some are reversible, some are not reversible. For example, if I have a piston arrangement again like this, and if I have two bars, let's say this is a hot bar and this is a cold bar. So if imagine that this particular cylinder is filled with some gas. Now, if I keep this hot bar under this piston, what happens? The heat from this particular system, that is Q from this particular system, is absorbed by the piston, is absorbed by the chamber, and the gas expands, which means the piston will go up. Now, immediately if I switch it to a cold bar, what will happen? Then heat from this particular system will reach the cold bar. The heat from that particular system will reach the cold bar because of the fundamental laws of thermodynamics, and then immediately the piston will come down as the gas compresses because it is losing its energy. The hot bar will give it energy so that it can expand. The cold bar will take away energy from that particular chamber so that it compresses. So I'll keep the hot bar, it expands. Then I'll remove the hot bar, keep the cold bar, and it compresses. Right? So that is a process that is happening here. Now tell me, if I reverse that particular order, instead of keeping the hot bar first, what if I keep the cold bar first? Then again it is possible, right? Because even if I start from the cold bar, the same thing happens. Again, it compresses. If I give the hot bar, it goes up. So that particular process is reversible. I can do it either in this order or I can do it in this order. Both are possible here. So that kind of processes are known as reversible process, and which is not possible like this. For example, if I burn a piece of paper, I cannot unburn it. So that kind of processes are known as irreversible processes. So again, we can see that a process that can be reversed exactly, that is, returning both system and surrounding to their initial or original state without any effect, then that is known as a reversible process. So this is known as a reversible process. And if the system does not return to its initial state, that is the original state, then we can see that that is an irreversible process. And the examples for reversible processes are a heat engine. I'll tell you what a heat engine is, and a quasi-static process, that infinitely long process we studied about. And for irreversible process, we can say that all spontaneous processes, that is combustion and any other spontaneous process that is happening in nature, is an irreversible process. It is increasing the entropy. So we can say that all spontaneous processes are irreversible in nature. So now, what exactly is a heat engine? A heat engine is something that works on the principle of thermodynamics or simply uses heat to work. For example, you can imagine the engines, that is the steam engines that was used in earlier eras. That is, a train used the steam engine to run. That is, you might have seen the choo-choo trains which was running on steam engine. So just like that, Titanic also was running on a steam engine. You can see big boilers and steam coming out of it. So that was also running on a steam engine. So all these were based on the heat engine principles. So what exactly is an heat engine and how is that related to our thermodynamics chapter? So what exactly is a heat engine? Just before, I showed you an example where the piston goes up and down when it came into contact with something hot and something cold. So that particular process itself is the working of a heat engine. That is, if you have a system like this, let's say this is your system and this is your cold reservoir, that is your cold part, and this is your hot reservoir, that is, this is where heat is being supplied, then we can say that the system can absorb Q1 amount of energy or Q amount of energy from this particular hot reservoir, and this energy will be used in order to do some work. That is, the system will do some work. Let's say that if this is the exact arrangement, this is a piston and here it is filled with gases, completely filled with gases, and I'm bringing a very hot body in contact with this particular piston, then automatically the gases expand. When the gases expand, the piston moves up. If I connect this piston to some other arrangement, which, let's say, in order to lift something, to lift this particular load, if I connect this, then what happens? As the piston moves up, this rod moves and this load will be lifted. So just like that, I am doing a work on the surrounding, or I am making the system do one particular work, and that is achieved by giving energy to this particular system. So again, I can say that. So the hot body gives Q amount of energy to the system, and that energy is used to do some work. Now again, this is going up, but I want to put it down now. So what will I do? I have to move the piston down. So what can I do? So I have to compress the gases. So that is where the cold reservoir comes into play. So the cold reservoir again absorbs energy from this particular system. That is, the system now gives Q amount of energy, that is Q dash or Q1 amount of energy to the cold reservoir so that the entire piston compresses. So the system gets energy from the hot reservoir, it goes up and it does some work, and then when you bring the cold reservoir in contact with the system, certain amount of energy is absorbed by the cold reservoir, the piston comes down. So this particular process can be repeated, right? Then you have a perfectly good working engine. But the only problem is that that is an ideal engine. That is because you don't have perfect temperature in order to produce that particular effect. That is, yeah, you can heat up, let's say you can heat a system to 2000 degrees Celsius or 5000 or 10,000 degrees Celsius. That is fine. So you're heating it so hard that it goes up a really long way. Fine. But to produce that particular perfect temperature exchange, that is, in order to bring this down, the piston should compress really well, which means a perfect level of coldness should be supplied. That is absolute zero. That concept also came from this particular heat engine. So the concept of absolute zero is not practically possible, right? Because the absolute zero value is minus 273.15 degrees Celsius. And that is not really attainable. That is 0 degree Kelvin is not attainable by our standards, and it is very difficult also. So it is not practically possible, but theoretically it is a very good engine. So this was actually found out by Carnot. That is, he was French physicist, and that's why this is known as a Carnot's engine, which we will study very soon. But again, the working of a heat engine, this particular concept was observed and tried to be applied by Carnot, which he failed miraculously, but again the concept was brilliant. So let's see how that particular process can be converted, or simply how he idealized or visionized how that particular heat engine would work. That is, without any loss, without any energy loss, how would that particular system work? Because Carnot imagined that, okay, the piston will go up, down, if I keep on exchanging hot and cold bars. If I keep on exchanging hot and cold bars, perfectly compressing and expanding the system, then I have a very good heat engine, which is again better than all the steam engines out there, because the steam engines provided an efficiency of 16% or something. So this particular heat engine would provide an efficiency of 100% because all the energy put into the system is now being converted into work. He forgot to account that there is friction, there is mechanical wear and tear, there is vibrations and certain other sorts of energy losses. So he assumed that, okay, I'm going to disregard all of this because my entire energy is going to be converted into work. That was not actually possible. Now also that is not possible. But this was a theoretical concept which certain other scientists like Lord Kelvin also contributed to. And that is how the theory or the branch of thermodynamics actually bloomed. So again, this particular system, how it should have worked according to Carnot is what we are going to study here. So let's imagine that we are inside Carnot's head and we are going to study how this particular system works. That is an ideal heat engine which converts 100% of energy given to that system into 100% of work. So how does that ideal heat engine, or simply Carnot's engine, that is, it is also known as Carnot's engine. How does that Carnot's engine actually work? So the first step is expanding the gas. The expansion should be isothermal. So the first step in constructing Carnot's engine is that we have to expand the gas, and that is isothermal expansion. So the gas is going to expand isothermally. So the gas is absorbing Q1 heat from hot reservoir at temperature T1 and it is expanding. So again, we are using heat to do a work here, right? We are giving heat to a particular system and the system is doing work. And to this particular point, we were doing work and then we were getting energy instead. Now we are going to see how we can give energy to a system and the system is going to do the work. So which means that we are giving heat to a system and the system is going to do a work, which means we can write down the equation for work done. That is the first work, which is isothermal expansion, and that is given by the equation which we studied earlier, that is nRT ln V2 divided by V1, and here it is happening at temperature T1, so I'm going to take it as T1. So nRT1 ln V2 by V1 is the equation for isothermal expansion. And the second step is adiabatic expansion. That is keeping the energy constant. Now the gas is going to expand adiabatically. That is energy exchange is zero. The temperature is going to change, but the energy is going to remain the same. So again, imagine we are just going to predict how the system is going to work. So there was a gas in a container, and when you apply heat to that particular system, the system expands. Right. So that particular expansion, initially it was isothermic, which means the temperature is remaining constant. It is a very slow process. It is an isothermal process. And after that, it is adiabatic process, which means that after increasing or expanding without changing the temperature, now we are expanding without changing the energy, or simply the temperature is changing, but the energy is still remaining constant. So that is the expansion part. So the piston is going up like this. So two processes are happening there, that is isothermal expansion and adiabatic expansion. So here the gas is going to expand adiabatically from temperature T1 to temperature T2. Then again it is doing a work, so that particular work done is given by W is equal to, so that is given by W, that is W2. So W2 is equal to NR into T1 minus T2 divided by gamma minus 1. Now again, these two processes is about expanding. That is, the gas expanded inside the piston, causing the piston to go up. So that is half of the process. Now the piston has to come down. That is, the process have to repeat on itself. That is why the heat engine is a reversible process. Again, you can do this either this way or this way. Both are possible. So again, the piston has risen up right now. Now it has to go down. Now the piston has to go down, which means that the expansion part is over. Now it has to go to the compression part. So how does that compression happen? So just like this, that is, whatever happened this way, we are going to do it the other way around, which means that instead of isothermal expansion, now it is going to be isothermal compression. So the third step is isothermal compression. So what exactly is happening here? The Q2 amount of energy, that is, initially Q1 energy was given to the system. Some of that energy was used to do a work, and then the remaining energy, that is Q2 amount of energy, is now given to the cold reservoir. Remember, when the cold reservoir is in contact, the piston is moving down. So again, Q2 amount of energy is given to the cold reservoir, which is operating at temperature T2. So the cold reservoir is operating at temperature T2. Then we can say that work done W3 is equal to NR T2 into ln of V4 divided by V3, right? And finally, what is the last step? And that is step number 4, that is adiabatic compression. So again, in adiabatic compression, temperature is changing, but the energy is remaining constant, which means the work done W4 will be equal to nR T2 minus T1 divided by gamma minus 1. So these are the 4 equations for the work done in a heat engine. That is, in the case of our ideal heat engine, these 4 processes will be responsible for the work done. That is, the piston expanding and compressing. What are all happening inside that particular piston? So there is an isothermal expansion, an adiabatic expansion, and then there is an isothermal compression and then an adiabatic compression. When the energy is absorbed from the hot reservoir, the piston is expanding isothermally. So again, there is an exchange of energy there, but the temperature is remaining constant. And then it is expanding adiabatically. The energy is remaining constant, but the temperature is changing. And after that, the piston has gone up. Now it has to come down. So in order to make it come down, that is, the piston went up, did some work. Now the piston has to come down. So we introduce a cold reservoir. So when we introduce a cold reservoir, there is isothermal compression. That is, energy is now given to the cold reservoir. Q2 amount of energy is now given to the cold reservoir, and now the temperature is same. After that, when the energy exchange is over, we have an adiabatic compression. That is, temperature is now changing, but the energy exchange is no longer there. So that is the entire process of a heat engine. So essentially, we have different forms of work here, that is W1, W2, W3 and W4. And if we add all these individual works together, we will have a net work that is done. So we also have to find out what is that particular net work done. But before that, graphically also we can represent this particular process. So if I draw a graph, that is a PV graph, because P delta V is again work done, or PV is just work done in thermodynamics. So any area under this graph will give work done. So we can use a PV graph in order to represent what happens inside a heat engine. So what happens initially? Initially it is isothermal expansion. That is, here it is P1, V1, T1. And now it is expanding isothermally. So it is expanding. Expanding means pressure is changing, volume is also changing. The change in pressure is comparatively low because temperature is remaining constant, but the volume is changing. So we can see that. So from P1, V1, T1 to P2, V2, T1, the gas expanded isothermally. So this expansion part is isothermal expansion. Isothermal expansion. And now this is isothermal expansion. And the next step is adiabatic expansion. So what happens in an adiabatic process? The pressure, volume and temperature altogether change. But it is not a drastic change. So it is going to be a small change like this one. So here we have P3, V3 and T2. So this is adiabatic expansion. Now again, what happens? This is the part where the piston goes up. Now the piston has to come down. So when the piston comes down, the volume changes. So we can see that after this, there is isothermal compression. So isothermal expansion was like this. So compression will be like this. So here it is isothermal compression, which means that it is now at P4, V4, but temperature remains constant. So this is it. And finally, there is also adiabatic compression. So here we have adiabatic compression. So initially it was isothermal expansion, adiabatic expansion. Now it is isothermal compression and adiabatic compression. So this entire process, this cyclic process completes the heat engine's work done, or simply the processes that is happening inside a heat engine. Now we also have to find out what is the net work done, and that is W net, which is equal to W1 plus W2 plus W3 plus W4. That is isothermal expansion work done, adiabatic expansion work done, isothermal compression work done, and adiabatic compression work done. So if you add up all these works together, we will get what is net work done. The only problem is that you have to watch for the sign, because initially, even though it was a positive sign, that is positive work done, it is happening in one direction. It is that the work is done by the system, so we are taking it as positive. But when the work is done on the system, we'll take it as negative. So when it is coming down, that is when it is isothermally compressing, we'll take it as negative, because again, work done by the system is positive, work done on the system is negative. So which means that W4 is actually negative, and this will be equal to W2, because both are isothermal processes. That is, the equation for W2 and W4 are very similar. That is, the equation is NR into T2 minus T1 divided by gamma minus 1 for W4, and NR into T1 minus T2 divided by gamma minus 1 in W2, which means that if I take a minus sign common for this particular W4, both the equations are same. Or I can simply say that W4 is equal to minus W2, or simply minus W4 is equal to W2. So I can write this particular equation as W net as W1 plus, instead of W2, I can write it as minus W4, or I can also write it as W2 only and take W4 as minus W2. I can write it in both ways, both are same, so that W2 and W2 cancels each other out. That is the work done during an adiabatic process, and the work done during the adiabatic process, that is during compression, cancels each other out. The work done during adiabatic expansion and the work done during adiabatic compression both cancels each other out, and the only thing we have remaining is W1 plus W3. That is isothermal expansion and isothermal compression, because in the other stages there is no exchange of energy, hence there is no work done. So again, remember, during the adiabatic process, it is no work done. During the isothermal process, there is work done. Just remember that one, that is, during the isothermal process, there is work done. During the adiabatic process, there is no work done. So this W1 plus W3 can be written down as nRT1 into ln V2 by V1 plus nRT2 ln V4 divided by V3. Then again, you have to remember that W3 is also negative here, because again, remember that which process is positive and which process is negative, because when the piston is going up, we are doing the work done by the system. So when the piston is going up, all works are positive, which means the expansion stages are positive. But during the compression stage, the surrounding is doing a work on the system. So since the surrounding is doing a work on the system, we'll take it as negative. So during compression stages, we'll take both as negative only. So we can just say that here, this particular quantity, that is W3, is considered to be negative. Then we can simply write it as W net is equal to nRT1 ln V2 by V1 minus nRT2 ln V4 by V3. You can take the nR's common, but up to this point also is enough. And the last part we have to do is that what is the efficiency of this particular heat engine. So what is efficiency? Efficiency means that efficiency, which is indicated by the Greek letter eta. So efficiency is indicated by the Greek letter eta. It is actually a ratio of output power to the input power. That is, how much are we inputting and how much output are we getting for that particular input. So we can say that output divided by input is the efficiency of a system. If you're giving 100% fuel to a particular system, how much of that fuel is it able to convert into work? So that is, if you're giving 100% energy to one particular system, how much of that energy is it able to convert into work? That particular measurement is known as efficiency. So we can see that in this particular case, that is in the case of a heat engine, we can say that the output we are getting is work done. It is work done, and the input we are putting is Q1. That is the heat we are supplying to that particular system. So work done by the energy supplied, we will get our output. So work done can also be written as the change in energy. That is how much energy we have given, that particular difference that is remaining will give us the work done. So we can say that from the initial energy what was given to the system and the energy what was returned to the cold reservoir, if I take the difference, then automatically I'll get what is the energy that is used for work done, or simply this particular equation will give me what is work done. That divided by Q1 will give us the efficiency. So I can write it as Q1 by Q1 minus Q2 by Q1. Right. So I can write it as 1 minus Q2 divided by Q1. This is the equation for the efficiency of a heat engine. So again, mainly problems are asked from this particular equation. So instead of energy, we can also use the term of temperature here. That is 1 minus T2 by T1 can also be used in order to represent the efficiency of a heat engine that is working. That is all about thermodynamics in this particular session. You just have to remember that no engine is more efficient than the Carnot's engine, because it is an ideal engine where entire heat or energy that is given to the system is converted into work. But that is not actually possible. So working between two temperatures, that is T2 and T1, no engine is more efficient than the Carnot's engine. But that's it for today. I'll see you all very soon with a new chapter. Until then, thank you.